So good evening, everyone. This is number theory session, and we'll start with prime numbers. Okay, so far what we have done is divisibility. And what are the definitions? Some number d, which is non-zero, divides number n. This was our symbol. If n is equal to d times some integer q, right? And in that case, we say d is divisor of n. So two sure divisors of natural number n are 1 and n itself. 1 and n itself are always divisors. For a positive integer. And in fact, some numbers are so special that they have only these two divisors, 1 and number itself. And such numbers we call as prime numbers. Yeah, let me go to next page and I'll write definition. So for example, let's see, say number 2 and only divisors are 1 and 2. And such number we say is prime. Then next 3. Only divisors are 1 and 3 itself. There is no other divisor than 1 and itself. Okay. 4. For 4, 1, 2 and 4. So there is a divisor other than 1 and 4 itself, right? So this is not a prime. Is that okay? Yeah. So let's write precisely the definition. An integer n greater than 1. An integer n greater than 1 is called as a prime. Prime number. If its only positive divisors are 1 and n itself. Or in other words, shall I say equivalently, an integer n greater than 1 is a prime number if it has exactly two divisors. Fine? So that is, it has exactly two divisors. And by divisors, I mean positive divisors, and has exactly two positive divisors. Yeah, so that's our definition of prime number. Just quickly copy down the definition and we'll go to next page and write down one or two remarks on the definition. Can I go ahead? Let's say remarks. An integer n greater than 1. Integer n greater than 1. Which is not a prime. Is called as a composite number. It's called as a composite number. Fine. Now look at the definitions carefully. So number 1 is by definition neither prime nor composite. So 1 is neither a prime nor composite by definition. You can define the things the way you want. So we define 1 neither as a prime nor as a composite. In fact, such elements are called as units. 1 is called as unit or unity. And you see that
The thing is, if we called one a prime, then it would break the fundamental theorem of arithmetic.
yes.
And if we call one a composite, and then a composite is equal to a composite into a composite, and it will go forever. So the simplest way is to say neither.
Yes. Yeah. Okay. Now for all of just a minute. Bhairav,
I thought one was a unit because one has an inverse within the integers.
Yes. So 1 and minus 1 basically have inverses. Yeah.
Thank you.
Yeah. So for all of you now, first job is write down primes. Right. Primes between 1 and 100 in your notebook. Don't write in chat box. So they'll be useful even later. So write down in your notebook 1 to 100 in your notebook. Don't write in chat box. Yes, Bhairav?
Sorry, I forgot to lower my hand.
Okay, yeah. Vivan?
Sir, if so we are taking integer, so won't zero, then what will zero be? Will it be prime or composite or neither?
See, in fact, we are talking of only positive numbers. So, in fact, classically, all these things were uh, developed by essentially people before Euclid or like Pythagoras and so on. So, in those days, they were not dealing with negative numbers. So, by number, they meant only always positive integer. So, generally, these things are defined for positive numbers.
Okay. Thank you, sir.
Yes, Siddharth.
Nothing, ma'am. Sorry, nothing, sir.
Oh,
I just wrote my primes down.
okay. Siddharth, you can count how many primes are there and maybe you can write down in chat box, not for everyone, only to me, the number of primes. The number of primes between 1 to 100.
Got it, sir. I counted.
Yeah.
I'm sending it right now.
Yes. Yeah, that's correct.
Thank you, sir.
And your answer is one more than the actual answer. Chidan, yeah, correct. Who is this first one? Lasaya, yeah, your answer is correct. Shreya, Anish, answers are correct. Karthik, answer is much more than actual answer. Yeah, Kirti, that's correct. Diksha, that is correct. Maheshwari, that is correct. Vallabh, yes, correct. Vivan, check it again. It's you have not counted one number. Yeah. So I think this much time is enough. So see that if you have written all the primes, there are 25 primes. 25 primes between 1 and 100. And there is a nice technique, a simple technique for school level called as Eratosthenes sieve for finding the numbers. Yeah, so Eratosthenes was somebody's audio is on. Okay, so Eratosthenes was the chief librarian of a library at Alexandria. Where is Alexandria? Egypt. So he was a chief librarian, and he is more famous for his measurement of circumference of Earth in those days. So his period was a little before Euclid. So I think around 276 BC to 194 BC, approximately. Yeah, so he measured the circumference of Earth. Uh, so which is correct up to so error is less than 1% than what we know today with today's measurements and today's equipments. So he gave a nice method to find primes up to given number n. And the method is as follows. So I'll write on next page. But before that, let's do one small result. If number n, and by number n usually in this chapter we mean positive number. So if number n has no divisor, up to root n, then n must be prime. Yeah, so small justification of that or proof. So suppose n is AB, or I mean suppose n is not prime. So we are doing by contradiction. So n is not prime means n has some factors AB other than 1 and itself. Suppose n is equal to AB, where AB are other than 1 and n, right? Then what we know is by condition A must be greater than root n. Up to root n there is no prime factor. I mean no divisor. So A must be greater than root n. B must be greater than root n, and which implies product AB must be greater than root n into root n. So that is n, and we are saying n is AB. So I get n strictly greater than n. Is that a contradiction? Number can't be strictly greater than itself. Fine. So n can't be factored as some AB, where AB are other than 1 and n. So which means n must be prime. Yeah. So if I want to check, say for example, number number 100, whether it's prime or not. I should check by divisors up to root 100. So I should check by 2, 3, 4 up to 10. Yeah, I should write no divisor greater than 1 up to root 10. So by divisor, so what should I say? Proper divisor greater than 1. 1 is always a divisor. Yeah, shall we go ahead? So method of erasation is sieve. So what you do is write down all numbers. Suppose I want to find primes between 1 and 100. So I'll write down all numbers between 1 to 100. Yes, Ritvik? Ritvik? Yeah, raise the hand, Ritvik. Yeah, so we'll write down numbers up to 100 first. 46, 47, 48. You can also write down in your notebook. 59, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 67, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. Yeah. Now the idea is following. 1 is not prime by definition, right? So we'll cross 1. And the first uncrossed number, that is prime. That is 2. So 2 is prime. Now once 2 is prime, multiples of 2, 4, 6, 8, 10, and so on, they can't be primes because they are some proper divisor 2, right? So cancel out all multiples of 2. Like 4, 6, 8, 10, 12, 14, 16, 18, 20, and so on. So cancel out all multiples of 2. So essentially even numbers, ending with 2, ending with 4, they can't be prime. Ending with 6. Because someone's audio is on. 28, 38, 48, 58, 68, 78. These are surely not primes. They are multiples of 2 and they have a proper divisor 2 itself, right? So now the very first uncut number, that is prime. What is that? 3. So 3 is prime. Now do the same thing with multiples of 3. So cancel out, cross out all multiples of 3. Some of them already we have crossed in multiples of 2. So all even numbers are crossed already. Cross out odd multiples of 3. So what are they? 9, 15, 21, 27, 33, 39, 45, 51, 57, 63, 69, 75, 81, 87, 93, 99. Right? So we have cancelled all multiples of 3. And now again, first uncut number, that is prime. So how far we should go? Since we want to find numbers between 1 to 100, max to max we have to check divisors up to root 100, that is 10. So check up to 10 and rest all uncut numbers will be primes. Okay. Yeah, so cancel out all multiples of 5 which are still uncut. So they are essentially odd multiples of 5. 55, 65, 85, 95. And the very first uncut number is prime. Cancel out all multiples of 7 now. Check which we haven't cancelled so far. I think 49, 77. What else? 81. Yeah. Again, the very first uncut number is prime. That is 11. Cancel out all multiples of 11. And they are all cancelled. So check here. 11, 22, 33, 44, 55, 66, 77, 88, 99. Right? And we have reached up the limit of 10. So now whatever numbers are left, which are uncut, they are all primes. Right? Let's quickly circle them. 13, 17, 19, 23, 29, 31, 7, 51, 57, 53, 59, 61, 67, 71, 79, 83, 89, 97. So count if they are 25, then we are correct.
Sir, 43 and 73.
Oh, okay, okay. Yeah. 43, 43 and 73. Yeah, thank you. So check, are they 25 now? So here there are 4 numbers, 2, 3, 5, 7 in first 10 numbers. These are again 4. Then in next 10 there are only 2. Next again there are only 2. Then we have 3 here. again 2 here, we have 2 here, we have 3 here, we have 2 here, we have only 1 here. So see that the spacing is not uniform. In fact, in first 10 numbers there are 4, in next 10 there are 4, but later on it decreases, say like 2, 2, and then again it increases 3, 2, 2, 3, 2, 1. Right? So these, yeah, so these are 20 points, right? That's a very simple but interesting method, very useful method. We go ahead. Yeah. So then look at some observations. 2 is the only even prime, right? That should be obvious because once 2 is prime, all its multiples are obviously composite, and therefore even numbers are composite. Right? So 2 is the only even prime. All other primes are odd primes, right? Then as far as spacing is concerned, so just see between first two numbers, first two primes, there is difference of 1. Next, there is difference of 2. Again, difference of 2. Next, difference of 4. Now, see that again, the difference decreases. It again, from 4, it goes down to 2. And from 13, next is 17. The difference is 4. Again, it goes down to 23, that is 4. 29, that is 6. It increases. Again, it decreases. And in fact, you'll find at many places there is a difference of 2, right? So such primes are called as twin primes. So if p and p plus 2 are both primes, we say pair p comma p plus 2 are twin primes. Yes, Gaurav?
Sir, do the number of primes go on decreasing as we count higher and higher?
Yeah, that's a good question. Yes. So we'll come to that. But in fact, there is a nice result due to Euclid that there are infinite many primes. So number of primes is not finite; it's never ending.
So how can you prove that?
Yeah, we'll do that. Huh? Okay, so Gaurav has raised a nice question. For the timing, let me just note that number of primes is infinity. There are infinite many primes, and there is a conjecture. So that's a proved result, and if proof is simple, we'll do that. There is a conjecture that there are infinite many twin primes. In fact, there is a more general conjecture. So once again, conjecture due to the Polignac. So there are infinite many primes of the form p comma p plus 2k. So p plus some even number 2k. So there are infinite many such pairs. And you see if k is 1, that gives me twin prime, right? infinitely many such pairs. Both P and P plus 2k both primes. Still, that's a conjecture. It's not been proved or either disproved. In fact, there are many conjectures related to primes.
So, but how is this a conjecture if we don't even know it's true?
Yeah, conjecture is something which is neither proved nor disproved. So nobody has so far given any counter example, but still there is no standard logical proof. So such a statement is called as conjecture. So those mathematicians with their work, they have a lot of intuitions and they guess it. So it's just their guess. They couldn't prove it precisely in the logical form, but nobody has so far given any counter example also. So hopefully the results must be true. Or sometimes even guess can go wrong. Geeta?
Yes, sir. Can you repeat repeat the last line you mentioned, the
Oh, yes,
DC
yes.
equal
Yes. Yeah. So there is this twin prime conjecture that there are infinite many twin primes, and little more general was conjectured by de Polignac. So there are infinite many pairs where P and P plus 2k are primes for some given k. So for example, if k is 1, that gives me twin prime conjecture. So suppose for example, k is 2, so P comma P plus 4, there are infinite many such pairs. Or if K is 3, P and P plus 6, there are infinite many such pairs, and so on. Is that okay?
the value of K can differ or
Yeah,
anytime.
but I mean, we have to fix some K, and for that fixed K, there will be infinite many primes.
Sir, does P have a fixed value?
No, P is prime. So
Okay.
say for example, suppose K is 1. So P comma P plus 2, there are infinite many such pairs. Say for example, 3, 5, 5, 7, 11, 13, 17, 19, and so on. Everyone?
Sir, won't Euclid's axioms also be conjectures?
Axioms are actually not conjectures. So, yeah, that's a good question. Axioms are some statements which we assume to be true. So they are like basic rules. So they are not to be challenged.
Okay.
So axioms are neither for proving them. Right. So based on those axioms, what are results we state? That's our theory.
Okay, sir, thank you.
Siddharth?
So basically, our axioms combine. So if I understood this correctly, axioms are basically basic systems which cannot be challenged, and they make up this axiomatic system, right?
Yes.
But then if you take different axioms, won't it make a different system?
Yes. So for example, in geometry, Euclid gave some 5 in geometry. Instead of axioms, they are called as postulates. So
Yeah.
Euclid gave 5 postulates
Yes.
for geometry, and that fifth postulate was there were a lot of debates on fifth postulates, and just by changing fifth postulate, you get different geometries.
So basically, just changing one axiom can change an entire
Yes.
system. Oh, okay. Thank you, sir.
Sir?
Yes.
Yeah. So are there more composite numbers or are there more prime numbers? As like the numbers tend to infinity, like will the ratio of composite numbers always be greater than that of prime numbers, like number of composite numbers?
Yeah. So in some sense, actually, composites are more. But see, in case of infinity, you can't say something is more, something is less. Like for example, Suppose I give you natural numbers 1, 2, 3, 4, and so on. Okay. And if I give you all even numbers 2, 4, 6, 8, 10, and so on. Now I can give a function map from one set to other set. So this is set of natural numbers, and these are all even natural numbers. Okay. So in some sense, you'll feel like set of even numbers is half of set of natural numbers, right? But I can give a 1 onto map from set of naturals to set of even numbers. Like 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. And essentially, what is counting? Counting is essentially this. You give some map or relation between two sets, which is 1, 1 and on 2. Right? So, so for example, here is map which is 1, 1 and on 2 from set of natural to set of even numbers. So in some sense, this says set of even numbers or number of even numbers is same as number of natural numbers. Many as natural numbers. So in case of infinity, you can't say something like that, like something is more, something is less. But yes, as far as our intuitive ideas are concerned, in some sense, composites are more than primes. Yeah. Asriya,
Sir, we can actually I have proved that not that there are more composites, but the number of primes is less than or equal to the number of composites.
okay.
We
So
can just have a bijection where each prime is mapped to its square.
yeah, yes, that's good. Yeah.
So I'm not sure if this is actually valid, but I've like found something out. When you take any number, you multiply it by 2 and you add 1 and you keep on doing that, you will always like end up with a prime number specifically. What?
So you are
That's
doing 2n plus 1, right?
yeah.
Doubt. I'll think about it. I doubt.
But sir, if n is 7, then it should not work, right?
Pen is 4 also.
No,
No, I'm
for
saying you keep on doing it and
no,
then
even for 7 to the 14 plus 1, 15. Now next step is 31, and that is prime.
Oh, so if you keep going on, then yeah.
Yeah. Yeah, I'll think about it. Huh? This is
Sir, that would probably be because that all even numbers above 2 are not prime, they're composite. So you're getting all odd numbers when you're doing 2 and plus 1. So
yeah, we'll be getting odd numbers. That is fine, but at some point we get a prime. That's interesting.
Sir, I think the method which he told works because I tried with using I tried in the continuous flow and it works.
I mean like
So
the probability of it like ending in a prime number will be large because like you're keeping on doing it, right? So
yeah, only thing starting with some n. How many steps we should do that won't be there won't be any formula that won't be like fixed for it. Yeah, I'll think about this. Huh? This is new to me. Siddharth, your hand is raised. Sudarshan. Darshan? Okay, one more interesting conjecture which is related to primes is Goldbach conjecture. So Goldbach in fact wrote a letter to Euler, and in that letter this result was mentioned. So still it's not proved neither disproved. It's a conjecture. So this was mentioned in a letter to great mathematician Euler, dated 7 June 1742. And there are two versions. One is strong, one is weak. So stronger one is due to Goldbach, strong Goldbach conjecture, which says every even integer n greater than or equal to 4 can be expressed as sum of two primes. So for example, let's do it for small numbers. So for example, 4 itself I can write as 2 plus 2. The two primes may not be distinct. 6 we can write as 2 plus 3, 3 plus 3. 8 we can write as 3 plus 5. 10 we can write as 5 plus 5 or 3 plus 7 and so on. Okay. Now how far one can check? So for example, in 1938, mathematician named Pipping or person, I don't know whether he was mathematician, Pipping verified manually. In those days there were no calculators, no computers. Verified till 1 lakh. So till verified for even numbers till 1 lakh. So each and every number, every even number up to 1 lakh, he checked that it can be written as sum of two primes. And later on, nowadays computers are available. So in 2013, Silva verified it using computers. Till 4 into 10 raised to 80, which is a very huge number. And till this number, there was no counterexample found, but still nobody has given correct proof of this. In fact, one Chinese mathematician has claimed that he has proved Goldbach conjecture, but so far it's not checked by experts or not approved by experts. Yeah, in fact, there is one interesting conjecture due to Dubner. Every even integer n greater than 4208 can be expressed as sum of twin primes. Yeah, this is something really interesting. So that was about the original or strong version of Goldberg conjecture. Every even integer n greater or equal to 4 can be expressed as sum of two primes. And in general, let me tell you, additive number theory is difficult because what we'll be doing is results related to multiplication, division, etc. So multiplicative number theory is comparatively easier than the additive number theory. The weaker version is following. Every odd integer greater than or equal to 7 can be expressed as.
So one sec, every even number can be represented as the sum of two prime numbers or two or more prime numbers. Could you just?
Two prime numbers.
Oh, okay.
Yeah, so every odd integer n greater than 7 can be expressed as a sum of three primes. And see why this is called as weaker. In fact, that original statement, which we have called as strong, strong surely implies weak. Okay, can you see that or can you prove that? What I have is this result, every even n greater than 4, I can express as sum of two primes. So I assume this, and what I have to prove this? Every odd n greater than 7, I can express as sum of three primes. Can we do that using strong? So I say once again, strong form implies weak form. Or if I assume this result, every even n greater than or equal to 4 can be expressed as sum of two primes. Using this, I have to prove that every odd greater than or equal to 7, I have to express as three primes. Shreya?
Sir, two things. First of all, r can be equal to 3.
Very good. Yeah.
And also, I had a question doubt in the previous, in the
Yes.
stronger form. Could you go to the previous slide? Yes.
For this one.
No. Yes. This. How can every even n be expressed as sum of twin primes? Because then that would mean we just have to divide by 2 and then like n minus 1 and n plus 1 will be the twin primes.
Yeah, so something like that. So given n, basically, n I can write as n minus 1 by 2. No, sorry, n is even, right? So n I have to write as some p plus p plus 2, right? So which means 2 times p plus 1, or p plus 1 is n by 2, or my p is n by 2 minus 1. Yeah, so some stage onwards it says essentially n by 2 minus 1 is prime. And I think this is equivalent to what he said. So some stage onwards with 2n plus 1 procedure, you get a prime.
But sir, what if n is an even number but not a multiple of 4? Then n upon 2 would be odd, and n upon 2 minus 1 would be even.
Yes, surely, yeah. So I think statement is not quite correct. I check this. I'm not sure whether this is correct or not. Yeah, I'll check this. Huh? Surely there is some problem with statement.
Sir, I think it should be every multiple of 4 greater than 4 to 0.
Every So instead of even, it should be 4K type. I'll check it. I'll check it. Huh? Yes, Ritvik.
So can you just show the previous slide?
Yes.
The previous after this, yes, sir. Wait. Done, sir. Thank you.
Yeah, so I think Shreya told the proof quickly with this one. So suppose my n is odd greater than 7. This is odd. So you look at n minus 3, that is even, greater than 4. And therefore, by strong principle, I can write n minus 3 as sum of two primes, p plus q, and which implies n I can write as 3 plus p plus q, right? I can write every odd greater than 7 as sum of 3 primes. Okay, shall we go ahead?
Sir, just a minute, sir.
Yeah. Yes, Gaurav.
Sir, I was not able to understand the Goldbach conjecture because if I'm saying, say, I take a number b and then I have it as the sum of two primes, p1 and p2, where I say that p1 and p2 are greater than 2. So then, say I add it to some. Okay, so b, I say I add it to some other now. Yeah, so b is equal to say q by 2. So that would obviously mean that p1 plus p2 is equal to q by 2. So then I can take the 2 from the left hand side to the right hand side. Then I get 2 into p1 plus p2. And p1 plus p2, considering that p1 and p2 are greater than 2, they would obviously be odd. So an
Yeah.
odd into 2 is equal to another number. So I was not able to understand the premise of the conjecture.
Let me go to next page. And we'll do some examples. So for example, suppose I have said 10, 10 I can write as 3 plus 7. Or let's say 12, 12 we can write as 5 plus 7. 14, 14 we can write as 7 plus 7 or 11 plus 3. As simple as that. So given any even number greater than 4, you can write it as sum of two odd primes.
Okay, sir.
Right? Yeah. So one more result which we'll be discussing later on as a whole lecture. So I'm just mentioning this is result due to Euclid. Yeah. Fundamental theorem of number theory or arithmetic. So right now I'm not proving it. Maybe that will be good exercise. So homework. Read the proof from some standard book. Maybe Burton or New Kerman. Yeah, so statement is following. Every n greater than 1, so we are talking of natural numbers, is either itself a prime or can be expressed as product of primes in a unique way. That's more important, in a unique way. Yeah, so I'll just give some examples which already you must have learned in your earlier levels of school. So proof is homework. You read proof from any standard book. There are many proofs available. And right now, I won't discuss much about this. That will be separate, one whole lecture later on. Yeah, so for example, let's say 18. 18 I can write as 2 into 3 into 3, right? And all are primes. So 18 I can express as product of primes and in a unique way, except the order. Maybe somebody can write something like this: 3 into 3 into 2, or 3 into 2 into 3, and so on. So up to order, they are same. I can change the order of those prime factors, but except that, essentially it's in a unique way. So I can't write it as something like, say, 7 into something, 5 into something. Once factors are 2, 3, they are going to be the factors. Let's say 19, and I say 19 is prime. So every number is itself a prime, or if it's not prime, it can be factored as product of primes.
So can you give the link for the proof? I can't seem to find it on Google. Like, where
So
did
both these books are available on this one, Google. So you give number theory PDF by Burton or Neven Zuckerman. Both are available on the internet. Or maybe if you want, you can simply give proofs of fundamental theorem of arithmetic PDF, and you'll get many proofs of that.
Okay, sir.
Okay. Now using this, we'll do one result. There are infinite many primes. There are infinite many primes. Yeah, again, there are many proofs. In fact, more than 100 proofs of this available on internet. And in our course, we learn at least 2-3 proofs for the same result. But right now we are giving Euclid's proof. And that was given almost 2000 years back. But still, it's valid to today's logic. And it's a very interesting and simple idea. Yeah. So his proof is something like this. Suppose if we know, say, primes P1, P2, Pk, finitely many, okay? Then using those primes, I can construct a new prime. That's the idea. So let P1, P2, P3 up to some Pk be primes So these are known primes. And now construct a number. So construct n equal to product P1, P2, P3, Pk. So product of all known primes plus 1. Why plus 1? So that I can surely say a number is greater than 1. It's 1 plus something. And every n greater than 1 is either itself a prime or has some prime factor, right? So let P be divisor of n, where P could be
Brackets, is it P1 into P2 into P3? So what?
So let n equal to product of P1, P2, Pk.
Oh, okay. Understood.
Yeah, so by fundamental theorem, either n is itself prime or it has some prime factor. So let P be divisor of n, where P is prime. And possibly P could be even n. So my claim is P cannot be P1. And nothing special about P1. The way we are claiming P can't be P1, on same lines, we can claim that P can't be P2, P3 up to Pk. So here we have got a prime which is different from some known primes. So if I know K primes, I can always construct or get a new prime K plus first prime. And this goes on and on inductively. That essentially says number of primes is not finite. So there are infinite many primes, right? Yeah. So suppose, so this we do by contradiction. Suppose P equals P1. Okay. So this implies P surely divides multiple of P1, P2, multiple of P1, right? So P divides P1, P2, so on up to Pk. Is that okay? If I say P is P1, P obviously divides multiple of P1. So P divides P1, P2, Pk. And also P divides N. So implies P divides the difference of these two numbers. And what is the difference? N is P1, P2, Pk plus 1. And our earlier number is P1, P2, Pk. So this implies P divides 1. Is that a contradiction? Prime divides 1. Because prime by definition is greater than 1. The divisors of 1 are 1 minus 1. Right? So P divides 1. That's a contradiction. So P can't be P1. Similarly, sorry. Yeah. So P can't be P1. Similarly, P can't be P2, P can't be P3 up to P can't be Pk, right? So I got a prime P which is other than P1, P2, Pk, right? So this says essentially if we know K primes, so P1, P2, so on up to Pk, we can find or construct a prime other than known primes, different from any of these P1, P2, Pk, right? So I get a K plus first prime. And this leads to essentially what? So if I know one prime, I can find second prime. If I know two primes, I can find third prime. If I know k primes, I can find k plus first prime. And essentially this implies there are infinite many primes, right? Okay, so let's try the procedure. So for example, let's start with P1 equal to 2. I know first prime. Okay. Now construct number n equal to, I know only P1, say P1 plus 1. And that is itself a prime. So I'll call this as P2. Okay. I'll call this as P2. So my P2 is 3. And I construct now new number n equal to P1, P2 plus 1. So that is 2 3s are 6 plus 1, 7. Now luckily this is again prime. I'll call this as third prime. See that this procedure skips some numbers, like for example 5 will be skipped, right? But anyways, we are not finding all primes. We are showing that there are infinite many primes. So even if we skip something, that essentially means number of primes is more than that, right? So I'll call 7 as P3 and n is P1, P2, P3 plus 1. So what is that? That is 43 and yeah. And that is again prime. So maybe I'll call this as P4. But note that this procedure won't give you always a prime. So you can go ahead and find n like this. Find some n at some stage. Some stage where n is not prime. Okay? Where n is not a prime. And then in that case, you get some prime factor and see that it will be different from earlier ones. I think next step will perhaps we get n other than prime. So like product of 2, 3, 7, 43 plus 1. And that n won't be prime. Yeah. So for this fact, in fact, there are many proofs, as I said, more than 100. And we'll be doing some more proofs later in our course. So far good, shall we go ahead?
Yes.
Yeah. So we saw one fact that there are infinite many twin primes. So gap between two primes gets reduced at that point. It just turns out to be 2. Like for example, 3, 5, then 11, 13, then 17, 19, 29, 31, and so on. So here the gap is just 2, right? But still, and how many such twin primes are there? As conjecture, there are infinite many such twin primes. But still, the spacing is in fact such that, suppose if I ask you some number, say for example 10, you can always produce 10 consecutive composite numbers. So there, the gap between two primes is more than 10. Okay, so the spacing is, what should I say, given any positive integer k, there exist k consecutive numbers none of which is prime. None of which is prime. So for example, suppose I give you say k equal to 4. And you produce 4 consecutive numbers, none of which is prime. And that is something small. So like 24, 25, 26, 27, right? Or for that matter, if somebody asks say k equal to 5, you can extend this same list by one more. So I get 5 consecutive numbers, none of which is prime. They are all composite, right? So gaps between primes are as large as we possible. Okay? Though at some points the gap reduces to 2. Is the statement clear? Yeah. So now before finding it for k, let's find, or you can try for say, suppose I give you 10, find 10 consecutive composite numbers. Find 10 consecutive composite numbers. You get it, you can write down in chat box to me. Let's say in between 29 is prime. So these are not consecutive. I want, without any break, some 10 consecutive numbers, all of which are composite. None of them is prime. Yeah, Diksha, good. Yeah. Yes, Maheshwari, good. Okay, so those who have got it for 10, we can try for some bigger number. Say 25 consecutive composite numbers. Yes, Ritwik.
Will it always start with 24, sir?
Which one will start with 24?
So you said that k is equal to 4. So you had like four numbers written. That is 24, 25, 26, and 27. So will it always start at 24? Will it start with some other number also?
No. It may start at any other. So just for 4, I started with just 24. So nothing special about 24. So maybe you can find something smaller than that.
I sent my answer, sir.
Just a minute. Maybe 14, 15. No. I think 24 is list for 4 consecutive. but of course there are many four consecutive composite numbers. So maybe 90, 91, 92, 93, right? Yes, Sriram, Vivan, correct. Okay. Good. Who else has given? Yes, Arya, yeah. Siddharth. Oh, Siddhartha, I don't know. Possibly your answer must be correct.
BTW, it just starts with this number. I'm just sending you in chat.
Okay.
One sec. I'll just make this a bit simpler.
Dhruva, 97 is prime. It's not composite.
I sent, sir.
Oh, yes, Siddharth. Yeah, good. Okay, so Siddharth has one nice trick. So the idea is following. You look at numbers, say for example, some a plus 2, where I choose suitably number a plus 3, a plus 4, a plus 5, and so on. So do you agree that these are all composite, right? And I'll choose a such that it's a multiple of 2, multiple of 3, multiple of 4, multiple of 5, and so on. So as many numbers I want. So like suppose I want 10 numbers, I'll choose a to be multiple of 2, 3, 4, 5, 6 up to 11. Why 11? Because 2 to 11 are 10 numbers. So I take it as product of, say, first 10, first 10 numbers greater than 1. So I choose A to be, for example, 10 factorial. Sorry. 11 factorial. Okay. And what speciality of 11 factorial is divisible by 2, 3, 4, 5, 6 up to 11, which are 10 numbers. So I consider 11 factorial plus 2, that's divisible by 2, 11 factorial plus 3, that is surely divisible by 3, 11 factorial plus 4, that's divisible by 4, and so on, up to 11 factorial plus 11, that is divisible by 11. So these are 10 numbers which are divisible by, say, 2, 3, 4, 5, 6, and so on. So they are all composite. None of them is prime. Or consecutive numbers, that's first thing, and composite. Right? So that's for 10 numbers. Now you can more generally give it for k numbers. Right? Yes, Bhairav?
Sir, actually, we can take the LCM of 1 to 11, which
Oh,
is
yes, very good. Yes.
27,720.
Yeah, good. LCM, yeah. So some number which is divisible by 2, 3, 4, 5, 6 up to, say, 11. Okay, fine. Yeah.
On the other hand, the lowest number of A for which A plus 2 all the way to A plus 11 are composite numbers is actually 112.
Yes. Yeah, so surely this procedure won't give us least set of numbers, but surely it gives us one such set of numbers. Okay, so more generally, if I want k consecutive integers, which are all composite, what should I do? K consecutive numbers, all composite, none of them is prime. So for 10, you started with 11 factorial plus 2 up to 11 factorial plus 11. Right? Why 11? Because 2 to 11 are 10 numbers, right? I can't start with 11 factorial plus 1. Okay. So for k consecutive numbers, what I should do is that I say k plus 1 factorial. And what is that? It's product of 1, 2, 3, 4, 5, 6 up to k plus 1. So it's divisible by every number 2 to k plus 1. Right? So this plus 2, k plus 1 factorial plus 3, k plus 1 factorial plus 4 up to k plus 1 factorial plus k plus 1. Right? What will be one number before that? K plus 1 factorial plus k. And these are k consecutive numbers. All of you agree? They are k numbers and all will be composite. This is divisible by 2. This is divisible by 3. This is divisible by 4 and so on. This will be divisible by k. This will be divisible by k plus 1. Okay. So these are k consecutive numbers which are all composite. None of them is prime. That's fine. Yes, Achyuta. Okay, shall we go ahead? Yeah, so there is one more function related to prime numbers, and that is pi of x. So pi of x stands for number of primes up to x. So for example, just in the start, we saw that pi of 100 is 25, right? Okay, so if I ask you what is pi of 100, that's a composite function. So that is same as pi of its inside value is 25. And what I mean by pi of 25, number of primes less than or equal to 25. How much is that? That is 4 plus 4, 8. And so up to first 10 there are 4. Then in next 10 there are 4. And then 21 to 25 there is one prime, namely 23. So shall I say this is 9? Yes, Edmund. Okay, so two great mathematicians, Legend and Gauss, stated independently in 1778 that number of primes up to x pi x is almost equal to, I'm not saying exactly equal to, almost equal to x by log of x. Okay. So I hope most of you know log x, but otherwise we'll be doing this function log x in our algebra course later. So for now, I'm not saying much about log x. So this is pi x is almost about x by log x. And it was proved. So they just stated the result based on the observations, and later on admired. And one more mathematician, I don't know how to pronounce that. Tala Valley. Poisson. So whatever. So the two mathematicians proved it using Riemann zeta function in 1896 independently. And later on, here this, and for here this, and Selberg again gave independently elementary proof. By elementary, we do not mean easy or simple. By elementary proof, we mean without using complex analysis. So the proofs were difficult. So around 1948, they independently gave elementary proofs of same result. Yeah, so that is about prime number theorem. So this is called as prime number theorem. Chitan, yes.
Sir, but it doesn't work for me. That comes as twice as random. What why is it?
Which one? Which one?
Sir, x by log x comes like 100 by 2, which is 50.
Just a minute. Let's make some tables. So, in fact, that log is to base e. So, yeah. So let's see some values like x log x. This is to base e. That's log from calculus. Let's look at x by log x and the pi x value. So for x equal to 100, this log is about 4.60 approximately. And then x by log x is up to 2 digits 21.71, whereas the exact value is 25. So the error is around 13%. But as your value of x goes on increasing, error goes on reducing. You can see that fact. So for example, if you take this as 1000, this is 6.91. This is 144.76. And actual value pi x is 168. So error is 13.7%. So error increases actually from 100 to 1000. But later on it goes on reducing. So for 10,000, error is 11.64. For 1 lakh, error is 9.45%. So essentially, the theorem says that as x increases, as x goes to infinity, that error tends to 0. Or pi x is very, very close to x by log x. Pi x is equal to x by log x in that case. Error goes to 0, so pi x goes to x by log x. Yeah, this is 9.21, this is 11.51, 51. This is 1085 point something. This is 8685 point something. The number is 1229 and 959. So as x increases, error tends to 0, and that's what is meaning of the prime number here. Okay. Of course, there are many interesting properties, and we haven't yet solved problems based on prime numbers. So we'll do that next time. Yeah, Shreya.
Sir, is the actual value always more than x by log x?
Yeah, that's a good question. Yeah. So generally, pi x turns out to be more than x by log x. Yeah.
Okay, sir, thank you.
Also, sir, is this the natural log or log x to the base 10?
This is log x to base e.
Oh, so natural log.
Yes, Ritvik.
Sir, why is there error?
See, in general, that x by log x will turn out to be some real number. It won't be always some integer. Whereas pi x has to be integer, number of primes up to x. Right? So there has to be obviously some error.
Okay, sir.
Okay, so we'll stop then.